Welcome everyone to the De-icing salt and alternatives in our ecosystem, cities and households webinar. I'm so excited to have you all over here. We also have our three panelists that you can see on my screen right now, but they're also on the videos on the side. Before we begin, I do want to start with an acknowledgement that we're located on unceded indigenous lands. The Ganyangehaga Nation is recognized as the custodians of the lands and waters on which we gather today. I'm based in Montreal, which is historically known as Tiohtià:ke, and it is historically known as the gathering place for many First Nations. This event is brought to you by Ocean Bridge. I'm an Ocean Bridge ambassador this year. Ocean Bridge is the education arm of Oceanwise Conservation Group that is based out of Vancouver, but they do a lot of research and education all over the world. And Ocean Bridge is their youth program for Canadian youth. And this program is funded by Canada Service Corps. This is a snapshot of the people that are joining us today. Majority of the people today are from Quebec and Ontario, but we also have people from almost every other province or territory in Canada, and some people are joining us from the US, from Maine, Massachusetts, and Pennsylvania as well. And I think all of these places do have a similar issue. You know, we all have snow, we all use de-icing salt or their alternatives. So this is quite a relevant topic for many of us over here for many months throughout the year. This is our reality for many, many months across many places. For some cities and territories and provinces, this starts all the way in September and then goes on until May or beginning of June. For some people, it's only December and January. But this is a big discussion topic across Canada. We have winter season and construction season. You may be partaking in some of these activities as well. I'm going to start with a quick overview of salt. The statement that is written over here, it's quite obvious that rock salt or de-icing salt is different from sea salt and table salt. But more details will be provided by our panelists later on as well. But most rock salt for roads is mined from underground seams of crystal salt, and it is formed from evaporation of ancient seas. Miners follow shafts underground and break out slabs of salt with dynamite and powered shoveling machines. Trucks or conveyors then haul the salt to crushing machines. And then salt is protected by tarps or stored in buildings. It's usually stored in heaps in those buildings. 5 million tons of road salt are used in Canada each year to mitigate ice and snow conditions on roads and to provide safer road conditions. It does not include the salt that is applied to sidewalks or parking lots, which together likely doubles that amount. And this also does not always include the salt that we put on our own driveways. Okay, but that's a big number, right? 5 million tons. What does that really mean? It means that it's equivalent to an average weight of 50,000 blue whales. And we applied this much salt into the environment every single year. But not all of us have seen a blue whale. But we have seen this blue salt packet. And that's a 1 kilogram packet of salt. And comparing that to 5 million tons, that's 5 billion packets. And we pour that on our streets, on our roads, on our driveways every year in Canada, much more than that actually. So this sort of gives you a relatable example, and the city of Toronto applies 150,000 tons of salt on its approximately 5,100 kilometers of roads. Montreal applies 130,000, so Montreal's much smaller than Toronto, but it applies almost the same amount, and you can understand why, because the climate is different over here. We get a lot more snow as well. And this is a point of reference from 2017, where Vancouver also applied 7,000 tons of salt, which is 7 times its usual amount. They get less snow than Montreal and Toronto. So it's understandable that they won't be in their 6-digit tons of salt. An important part of doing this topic as well, and I want to plug in what I do as well, My background is in sustainability, accessibility, and urban design. And this topic is of high interest to me as well, because something that I notice all the time is this tug of war between accessibility and sustainability. You know, we have these snow heaps all over our streets or our pavements as well. And it can be very difficult for parents with strollers. It can be difficult for people with reduced mobility, people on wheelchairs as well. And the best way is to make sure that there is less friction on the pavement. And sometimes the only option is to put more salt. But we know that it is not very sustainable. And you'll hear that throughout the presentation today as well. And this tug of war that keeps on happening between accessibility and sustainability is one of the reasons why I'm also pursuing this project, to bring you all these different perspectives. I can talk a little bit more about accessibility towards Q&A period if someone is curious about this component as well. But what ends up happening when we put all this salt in our streets is that this de-icing salt flows into stormwater ponds. It accumulates over time over there, and it flows through streams, rivers, and lakes. It also gets absorbed into the groundwater sources. This essentially impacts ecosystems of all these water bodies, and in turn, our grand ecosystem. And this does not just limit itself to water bodies. If you think about on our roads, we have vegetation, trees along our roads. When the salt water splashes onto them, it gets absorbed into that vegetation as well. So who are the stakeholders that are making all these decisions, all these policies, all this research? We have governments and policymakers. We have wonderful researchers who are trying to solve a lot of these issues. Some of them are related to environment. Some of them are related to architecture, infrastructure. Some of them are engineers as well. And that leads to engineering companies who are designing these snow plows, all these trucks that are effective and efficient in spreading salt throughout the whole area. We have snow and ice removal contractors. We have residents just like yourself. We have conservation authorities, and we have property owners. Those include landlords, but also condominium buildings, as well as large-scale housing authorities as well. And this is why we're bringing in 3 different speakers to our presentation today. I'll give a quick introduction of each one of them when we go through the presentation, but first is Ana Cucurieaunu. She will give us an overview of her presentation. We'll come back, we'll give an introduction for Dr. Grant Clark, and then we'll move on to Tisha Tan, who is from TRCA. So Ana is on a mission to improve our local biodiversity and develop sustainable communities. Her career started in the field of architecture, designing innovative buildings with the help of environmental data, after which she studied biology and researched the effects of our built environment on aquatic life. Currently, she works in the nonprofit sector, engaging newcomers with environmental programs. She's also the founder and executive director of Friends of Parkway Forest Park, a super cool grassroots group that helps communities connect with nature through art, science, and collaboration. Her academic training is in architecture from Ryerson University, majoring in building science, as well as a Bachelor of Science from York University in biomedical sciences. So Ana, passing it on to you.
Thank you so much, Omer. I hope everyone can hear me. Okay, great. So Omer, you've done an awesome job at introducing the topic and giving everyone a lay of the land. So thank you for giving me the opportunity to talk to you about the impact of organic de-icers on aquatic insects. This research was conducted with a wonderful collaboration between the Donini and Kelly Lab at York University, and a lot of hard work from my friend Fargo. So as Omer mentioned, I did start in architecture. I worked many years in designing buildings and using environmental concepts and science to design better buildings. And later on, I transitioned into understanding the effects of the buildings on our ecosystems and lived environments. And this is where I learned about mayflies, which are the animals that I actually ended up studying later on. So Omer is right. We use about 150,000 tons of road salt annually in Toronto to avoid epic car pileups such as this. Although Instagrammable, it's not fun. And some of the strategies that we use to remove the ice are abrasives, which are sand and sawdust and gravel and rock salt, as well as chemical de-icers that kind of help the abrasives to attach to the road and melt ice a lot faster. However, the chemical de-icers, they bioaccumulate in the waters and in our environment, and they have a negative effect on our ecosystems. So then we became creative and we derived these de-icers out of organic materials, such as cheese brines, wine remains, and corn and beets. So today I will be talking to you about sugar beets and how beet juice de-icing liquid is affecting our ecosystems. And hopefully you can, by the end of the presentation, you can see how it is interacting with the physiology of insects and decide for yourself if we need a better solution. So just to compare with the traditional rock salt, beet juice de-icing liquid has a less concentration of salt. It lasts longer on our roads, which is a good thing. Works at lower temperatures. It's biodegradable, which could be a good thing and a bad thing. And also it's anti-corrosive. And the way it works, it is creating this layer between the ice and water molecules and the road, and it prevents ice from being formed. And if you're curious about how it works, this is how it's being applied on the streets. It's a liquid material and it looks like coffee. And it smells very nice. It's very pleasant. Unfortunately, just like other de-icers, they do end up in our water streams, mainly because of how we design our roads and bridges. And this leads to changes in the aquatic consistency and chemistry of the water. Here you can see a map of the United States, and you can see that over 50 years, the salinity in many areas of the United States has increased drastically. And unfortunately, 50 years is not enough for animals to develop strategies to cope with these changes. And so a lot of them actually die. And Lake Erie is one of these water bodies that has been extensively studied, and it's also the focus of my study. And this is a mayfly nymph, and they live in Lake Erie and other tributary bodies of water. And the species that I studied was the Hexagynia lambada, and they're unique because they have these feathery looking like gills that you can see on the lower part of their bodies. In terms of their life cycle, they live for about 2 years in the ground, burrowing in the soil underneath the water, after which they emerge on the surface and they live for very few days until they find a mate and die. And this is when you see these beautiful swarms of mayflies that lots of people like to take pictures of. This is also why it's important to know that mayflies are a keystone species of our ecosystem, acting as food for many, many different other species like birds, amphibians, fish, because they do live in the water as well as outside of the water. Just like any other freshwater organism, mayflies, they have to maintain a constant ion concentration in their bodies in order for their bodies not to explode when they live in very dilute environments. So in order to do that, they use osmoregulatory organs such as Malpighian tubules, trachea gills, and the alimentary canal. And it's also important to know that mayflies, actually, they don't have a circulatory system like we do. They don't have blood vessels and veins. Their blood is basically throughout the entire body. So I like to think of them as cannolis. It's just basically a tube and a hard shell. What we know so far about mayflies is that sodium is being taken up through the gills, and then it's being excreted through the alimentary canal, and then potassium is taken up through the alimentary canal to compensate for the change in charge. Some preliminary studies that I conducted was to look at just quickly observe how beet juice de-icing liquid affects the water and the animals. And as you can see here, the beet juice actually accumulates towards the bottom of the cup where the mayflies actually live, because they live in the soil. It also creates this film on the water if the water is static. And it seems to not be too good for the digestive system of the mayflies. I also looked into the toxicity level of the beet juice de-icing liquid, and to do that, I exposed mayflies to increasing concentrations of the organic de-icer. And what we noticed is that as we increased the concentration from 0 to 5%, a lot of the animals started to die off. And for our experiments, we chose 3.2% concentration of the organic de-icer, where we got about 80% survival rate. So the first step in understanding the effects of the organic de-icer on the mayfly is to see if there's any change in the water. So here you can see through this graph that the black graph bars, they represent the beet juice de-icing liquid. And you can see ions are a lot higher in the water, which is their new environment. But interestingly, each ion is not high enough to kill the mayflies on their own. So the reason why a lot of mayflies actually die, it could be because they work synergistically. So the ions together, they have a more compounding effect. So knowing that the ions in the water change, we also wanted to see, do these ions actually get inside the body of the animal? So to do that, we looked at the blood and the hemolymph of the mayflies, and we saw that sodium, chloride, and pH increased significantly, but potassium stayed the same. So this tells us that ions are present in the water and they also get absorbed into the body. In order to understand what exactly is driving these changes in the bodies of the animals, we looked at the gills, because the gills are an osmoregulatory organ, but they're also exposed directly to the water. And so we used the scanning ion selective electrode technique, which helps us measure the flux of ions in and out of the gill. So here we saw that when you're actually exposing mayflies to beet juice or organic de-icer, you see sodium being expelled out of the gill or out of the body, where in fresh water, the animal is extracting ions from the water into the body. So it's complete reversal of function. And in the rectum, or the last part of the alimentary canal, the sodium is being absorbed. So to summarize, what you can see from these images is that actually organic de-icers, or the beet juice de-icing liquid, does have an impact on the physiology of the mayflies. And it changes the way sodium is being moved in and out of the body, forcing the animals to cope with their new environment. We also know that at 4.2% concentration, half of the population would be dying if they're exposed to this concentration. So this is important to know, because if we have a too high in the concentration of beet juice de-icing liquid in our waters, a lot of these mayflies can die, and it can affect and collapse a lot of the ecosystems. And here I want to leave you with this image, and I will share you the link to a really nice clip on how maybe we don't need to use de-icers to manage our roads, and maybe we just need to change the ways we think in terms around how we can do more things during the winter. So thank you.
Awesome. Thank you, Anna. I'm going to change this a little bit over here. Perfect. Thank you so much, Anna, for this insightful presentation. This is very, very helpful for us to understand the impact of de-icers, or an alternative as well, on the larger ecosystem, right? If you think about one water body and other water bodies and how it flows to many of them, it evaporates and then it still stays in our system, and it just spreads everywhere as well. And thank you for taking all that data and synthesizes it into sort of simpler conclusions and simpler things for a lot of the audience as well over here. Thank you for that. We do have a very quick question over here from Tristan. It says, did you look at the fecundity or just survivorship?
Oh, good point. Not a lot of information is known about mayflies, unfortunately. So we're very limited in terms of the research that we can conduct. But in terms of fecundity, you would have to wait for the mayfly to reach maturity, and that takes 2 years. So it's a little bit difficult because the mayflies that we used, the nymphs, they were at an intermediate stage. So not too young, but not too old. So it really depends, but you could look at the sex organs and see how they change. That would be very interesting, actually.
Awesome. Thank you so much, Anna. Okay, so Dr. Grant Clark, who is here with us today as well. He grew up on a mixed farm in central Alberta, Canada. He is an associate professor at McGill University, an affiliate member of the Baylor School of Environment and the TRCA Institute of Sustainable Engineering and Design. He's a past president of the Canadian Society for Bioengineering, serves on the editorial board of Canadian Biosystems Engineering, and reviews for numerous other journals. His research includes ecological engineering for optimal management of agricultural and municipal organic residues, and management strategies for nutrient use efficiency and greenhouse gas emissions reductions from biosolids amended soils in Canada. He holds a PhD in biosystems engineering from McGill University, and before that he did a industry cooperative BSc in agricultural engineering from the University of Alberta, Edmonton. So Anna, in her presentation, talked a lot about the ecosystem as well, and we're going to connect it with Dr. Grant Clark's presentation by looking at infrastructure elements as well as engineering elements, and sort of zooming in a little bit on the city level as well in our urban environments. So I'll pass it on to Dr. Grant Clark. I think you were able to share your screen now.
I hope so. How does that look?
I do see it. Awesome.
Great.
Thank you so much.
Well, you're very welcome. And thank you, Omer, for the invitation to talk today. And thank you, Anna, for your nice presentation. So I'm going to come at this topic a little bit sideways, but we'll make some connections along the way. So I'm going to discuss a project that my research group and I conducted with the City of Montreal a few years ago. So the title of our project is How to Improve Runoff Water Quality and Street Tree Health Through Better Tree Pit Design. And you'll see the connections very soon with our topic of de-icing salt. I'd like to acknowledge, first of all, the people in my ecological engineering research group who were instrumental in this project, one being Dr. Mariam Kargar and the other Marcelo Frozi, who did their PhD and MSc degrees respectively working on this topic. I'd also like to acknowledge that our ecological engineering research group is part of the Department of Bioresource Engineering on the McDonald campus of McGill University. So the motivation behind our project goes back to some big drivers of change in the environment. One is increasing urbanization, which comes along with our growing population and the tendency of people to want to live together because life is easier that way. And the other big driver is climate change. And both of these have an impact on the way our cities impact the environment and the way we live in our cities. So there are a couple of immediate problems that result from increasing urbanization and from climate change, especially in our part of the world, in southern Quebec. We're expecting, and we're already seeing, in fact, increased frequency of heavy rainfall events, more frequent thaw, freeze events during the wintertime. And we expect overall that as climate change continues to intensify, there'll be increased precipitation generally in our part of the world. So as a result, we have increased volumes of runoff water in our cities that we somehow need to manage. And since we're in a temperate climate, and as I mentioned, we have more frequent thaw and freeze events in the winter, we have more ice to deal with in the winter time. And of course, we do need to deal with the ice somehow. Ana mentioned that there are alternatives in how we deal with the ice. There may be alternatives in how we live in a winter city as well. But we have to confront the problems one way or another. Another result of the way we live in our urban centers is that along with increased volumes of runoff water that we have to manage, the water is likely to be increasingly contaminated as our cities densify, as there's more traffic, and we have, for instance, the wear from our tires and brake pads contaminating the environment. If we're using de-icing agents, those will also contaminate water that falls as precipitation or melts from snow in the spring, for instance. And then those contaminants are carried into the environment in one way or another. So throughout my little presentation, I'd just like you to think about the way that materials flow through our environment, where they come from, where they go, and what might happen to them along the way. And that really is a principal focus of our research group, of the Ecological Engineering Research Group, is to think about those material flows and how we can manage them. So we're looking at two problems: increased volumes of runoff water, and the quality of the runoff water. And we're thinking of ways that we can deal with those challenges. So this is a beautiful graphic from the Chesapeake Bay Foundation. And they're talking about the way we view our landscape, and specifically our urban landscapes. And they point out that we can consider the way we manage the landscape as a green filter, where we're emphasizing the use of green infrastructure or biological components of the environment, specifically trees and grass and shrubbery and healthy soils, to turn that landscape into a green filter. So as water falls on the landscape, it may pick up contaminants, and it undoubtedly will, from the air and from the surfaces it falls on. But then the water has opportunity to infiltrate into the ground. So we can build our cities to accommodate the infiltration of water through a layer of vegetation and healthy soil. And then that vegetation and soil can filter out contaminants as the water moves through the ground, and the water can then recharge our groundwater aquifers and ultimately move into rivers and lakes. The other alternative, which is perhaps the more conventional way of thinking about urban infrastructure, can turn our landscape into more of a gray funnel, where we're building infrastructure that has impermeable surfaces, so asphalt covered roofs, paved streets, concrete, and hardtop parking lots. Now that's convenient because the water, when it falls, is very quickly evacuated. It runs off rapidly into our storm sewers, for instance, and is evacuated away from the city, so we don't have to deal with the problem of too much water. And it also makes the surfaces more convenient for driving and walking on if we can keep them clear and dry. But of course, there's problems with that too. One is that our infrastructure, specifically our stormwater management infrastructure, has to be designed with enough capacity to handle those large volumes of rapid runoff. And that can be problematic, especially as we mentioned with climate change. Those volumes are increasing and extreme events are becoming more frequent as well. So there's more chance that our infrastructure will be overwhelmed, that we won't have the capacity to handle those big storm events. The other problem, of course, too, is that as all that water runs off the hard surfaces, it's carrying contaminant loads with it. And if those are evacuated directly to a water body through a storm sewer or through some primary or secondary treatment plant, those contaminants may be discharged into the environment without adequate treatment, and they can have a larger impact on the environment. So those are two scenarios. And you can tell I have a bias here, right? So I'm leaning more towards the green filter side in my work. So green infrastructure, as I mentioned, includes the intentional design of infrastructure with living organisms to help provide ecosystem services or benefits to human society through the activity of living organisms. And so some of the benefits that come from using green infrastructure for stormwater management through, for instance, building grassy swales along roads that allow infiltration, street tree pits that are designed as bioretention and bioinfiltration cells through which the water can flow into the ground. Those kinds of green infrastructure act in a few ways to modify the flow of water through the environment. First of all, if you have a mature canopy of trees or shrubs or even a grassy surface, some of that precipitation is intercepted directly by the vegetation and evaporates back into the air without even reaching the ground. The vegetation also retains the water, so it doesn't flow as rapidly across the surface, and it has more time to infiltrate into the soil. And once it's into the soil, if you have healthy living vegetation, then the root system takes up some of the water from the soil and evaporates it back into the air again. So all of these processes reduce the need to handle excessive volumes of water in our sewer systems. And finally, of course, the water can, if it remains in the soil, can infiltrate all the way down into the groundwater table. And as it passes through the vegetation and through the soil column, the hope is that the contaminants that it may carry, if they're biological in nature, may be degraded into metabolites or products that are less harmful to the environment, or perhaps even beneficial to the environment. Or if they're non-degradable contaminants like sodium, for instance, from de-icing salts or heavy metals, they may be retained in the soil, perhaps for a long period of time, as is the case with metallic ions like lead or copper, for instance, or for more mobile ions like sodium, although the sodium will move through the soil column quite quickly, the full load of sodium from the de-icing salts, for instance, in the spring thaw, will not be released immediately into the environment as it would if it were all directed into a storm sewer and discharged into a river or through a water treatment plant. Instead, the sodium remains in the soil for some time. And instead of being introduced into the larger environment as a sharp and a large spike in sodium concentration, it's introduced more gradually. So the impact of that event is lessened. So talking about tree pits specifically, the project that we were involved in was looking at alternative designs for tree pits so that the tree pits could accommodate a larger volume of water flowing through them and treat the water to improve its quality and also keep the trees happier. So there are a bunch of benefits from the design improvements that we were proposing. This is a picture of what you might consider to be a standard tree pit. And so for the past half century or century, when municipal engineers are told they need to plant trees, they'll first build the roadbed and the adjoining sidewalks, and they'll pack the soil so that it's structurally stable and the sidewalk won't crack and the road won't buckle. Then they'll go in with a backhoe and they'll dig out a 1 by 1 by 1 yard cube from that compacted soil. They'll fill it with dirt and they'll plunk a tree in the middle. And they maybe put a grate over the top of it. So you end up with a tree which is quickly root bound, which is essentially living in a bathtub surrounded by relatively impermeable material in which the water pools. So the root environment is anaerobic and tends to accumulate contaminants. So you end up with very unhappy trees with a very short lifespan. The alternative to this is to design tree pits that are essentially much larger. So they have a wider opening at the top. The soil is deeper. Often tree pits are designed to extend underneath the hard surface of the sidewalk. So there may be some kind of an engineered soil or a subsurface mechanical structure that supports mechanical loading on the sidewalk, but allows the tree roots to grow through. So I'll just turn on my laser pointer here. You can see in this example that all of these tree pits are in fact connected under the sidewalk below that hard surface. And that surface is also permeable, so the water can flow through it into the soil underneath. So there's more space under the sidewalk for the tree roots to grow. So they have a much larger rooting volume. That keeps the trees happier. It also achieves our other objectives in that it can accommodate a lot more runoff water flowing into the tree pit, both through the openings and through the permeable surfaces between them. And we've also filled that volume with improved soil. And we were looking specifically at increasing the amount of organic matter in the soil we used in the tree pits to see how that would impact the quality of water as it moved downward through the soil profile. So our project was in the Hochelaga-Maisonneuve region of Montreal. And we, with the cooperation of the City of Montreal, constructed 24 tree pits with improved design. And you can see we've got instrumentation in the tree pits for collecting water samples and soil samples. And we put some electronics in there to measure moisture content and temperature and that sort of thing. So the question we were asking was, does soil organic matter help remove contaminants, including sodium, from the water as it passes through the tree pit? And we ran the study for a couple of years, so we had several seasons of data. And this was the result of Marcelo Frosi's thesis. So we're looking at sodium mass flux. So this is the mass of sodium that flowed through a unit area of tree pit. So if you take a square meter of tree pit surface, what mass of sodium flowed through that per week? And we looked at it at 3 levels. We looked at the surface, then we went down to the middle of the tree pit, about 50 centimeters below the surface, and saw how much sodium flowed through the equivalent area there vertically. And then we looked at the bottom of the tree pit. And you can see that there is a difference between the tree pits that had the low organic matter in the gray bars and the tree pits with the high organic matter with the green bars. Now, what's important to notice here is the trend, okay? So we had high variability amongst our small sample size of tree pits, but the trend is interesting. So you can see there is a gradual reduction in the amount of sodium as you go down farther in the soil with the low organic matter. So it still has a tendency to retain the sodium near the surface. The sodium doesn't move down rapidly or immediately through the soil profile, but you can see that trend is much more pronounced in the green bars. So the answer to the question is, yes, even with a non-biodegradable contaminant like sodium, increasing the quality of the soil by providing more organic matter does help to retard the movement of the contaminant through the tree pit. So that sodium will never degrade, right? It's an element, so it will always be sodium. Once it's in the environment, it has to go somewhere. It's not going to disappear. The advantage of directing the runoff water into the tree pit and constructing the tree pit and providing it with a healthy, rich soil is that the movement of the sodium will be retarded. And so these extreme peaks and the harsh impacts on the environment will be ameliorated. So that was the outcome of our study. If this had been an organic de-icing agent, for instance, like the beet juice, retention of the beet juice in the soil profile would give the microbes living there an opportunity to start to break that down. Now, we can ask Ana whether or not the metabolites would have a better or worse impact on the environment, but it provides an opportunity for biodegradation to occur if it's an organic contaminant that we're looking at.
Awesome.
So, yeah, there we go. That's my conclusion, which I have already stated. So I'll keep my peace now.
Awesome. Thank you so much, Dr. Clark. This is perfect. I'll actually move on to Tisha's presentation. Awesome. So Tisha, who is over here with us, she works in the Education and Training Division at Toronto and Region Conservation Authority, short TRCA. As a community learning coordinator, she develops and delivers events and programs across the city of Toronto, providing meaningful opportunities that engage and educate the community. She has worked in environmental restoration and education for the last 5 years. Tisha is an avid lover of wildlife, as you can see in the photo here, with a passion for introducing communities to ways that they can contribute to environmental stewardship efforts and collective scientific knowledge. Her academic training is Bachelor's in Conservation and Biodiversity from University of Toronto and Master's in Environmental Science from University of Toronto. So welcome, Tisha. And I'm going to stop sharing my screen now. Let's see if you can share your screen as well. Thank you. Tisha, the floor is yours.
Great. Thank you so much, Omer, for that wonderful introduction. I'm going to be talking to you about road salt alternatives at home. So without further ado, let's jump in. For those of you who are unfamiliar with TRCA, or Toronto and Region Conservation Authority, we are one of 36 different conservation authorities here in Ontario, and we work together with municipalities, with the province, and with other stakeholders in the communities that we serve in order to protect and preserve the land, specifically the 9 watersheds that fall within our jurisdiction. And we do this by protecting and restoring natural areas. We also have teams that will monitor and report on the health of Toronto's environment. And for me personally, as part of the community learning team, I help run programs that teach a greater appreciation of the environment, as well as encourage people of all ages to get out and enjoy nature for their own health and well-being. So road salt is a growing concern in watersheds across the Toronto region. And as Dr. Clark mentioned, once road salt melts the snow and ice and does its job, it does not break down or settle out of water. Instead, it will just dissolve in the water and, using the water, move and flow from our roads and parking lots into our stormwater systems. And from there, it actually enters our creeks, our wetlands, rivers, and lakes. And that's something that we can measure here at TRCA. So through monitoring activities, we've identified that chloride levels in some of our urban waterways are at sufficient levels now to start to cause negative effects to our local vegetation and both terrestrial and aquatic wildlife. So I have here a map that gives kind of a more detailed look at some of the recent levels of chlorides in streams across the Toronto region. It displays the average chloride concentrations at water quality monitoring stations between 2016 and 2020. Now, I won't go over this in too much detail, but I do want to note that the highest levels of chlorides that we saw were found in the most urbanized industrial areas of our jurisdiction, of course, and the levels were peaking around the winter, spring. So that definitely tells us that road salts are very heavily involved in that. All of this data and more can be found on our Watershed and Ecosystems Reporting Hub. This is a really awesome resource if you're interested in learning more about chloride levels in Toronto, or looking at other water quality measures, or even just learning about the current environmental conditions of the Toronto region. So I've shared this with Omer to pass along to you if you're interested in learning more. Now, over the last decade, there have been some significant advances in winter maintenance technology and practice. This includes things like developing low chloride alternatives to road salt, like the beet juice that Anna mentioned, improving application techniques, and advancing our own abilities to monitor weather and pavement conditions as well. Now, so that means that winter maintenance practitioners now possess more tools in order to safely and effectively control snow and ice while also using less road salts. That's really great news. As residents and homeowners, we all have a part that we can play as well. So by implementing some of these strategies on your own property or spreading the word to your neighbors, friends, and family, you can also contribute to reducing chloride levels in our waterways. So what are we looking for when we're considering alternatives to road salt? Well, there are two main things that road salts do to help manage icy conditions. The first thing that they do is they create traction so that roads and sidewalks are less slippery. They also will lower the freezing point of water, which effectively melts the ice and stops ice from forming. So they do this by mixing with water to form a solution that has a lower freezing point than just water alone. So instead of freezing at 0 degrees Celsius, water and salt will freeze at temperatures as low as -10 degrees. Though due to different factors, our traditional rock salt is really only effective or is most effective at temperatures around -7 degrees Celsius. Now, of course, compared to some larger properties or municipalities and other road salt use, the amount of road salt that you are using, let's say on your own driveway or on the stretch of sidewalk just in front of your home, really barely makes a dent in the rising chloride levels that I mentioned earlier. However, it's always good to consider what you can do on your own property to help, no matter how small the impact. And there are a variety of different road salt alternatives that can help. As you spread the word to your friends and family, then that's just increasing the impact that you can make as a resident of the city. So let's look at alternatives that create traction first. Lucky for us, these are fairly affordable and they can often be found just around the house. So the important thing to consider is if you choose to use one of these products, they may not be the most effective since they're not actually de-icing. They're just increasing the traction. Also consider that there will be cleanup involved, or at least there should be cleanup involved if you want to be a little bit more responsible once the spring melt starts, because you still don't want some of these things entering our waterways in abundance. So for example, we've got coffee grounds, which creates traction. It's really nice that it's biodegradable. And in the spring, you can sweep it into your gardens or onto your lawn to kind of act as a natural fertilizer. If it doesn't get swept up, it can increase the amount of organic material that goes into our waterways, which can have a number of different effects, including eutrophication of those water bodies. Things like kitty litter, sand, and volcanic minerals like this Eco Traction product are really, really great at creating traction as well. But again, they need to be cleaned up after, and because if not, then it will increase the amount of sediment in water bodies, and this can have significant impacts on aquatic habitat quality, affecting, you know, some of the lifestyles of some of our aquatic fish species. Now let's talk about alternatives that will actually melt the ice. Something like alfalfa meal, which is a natural fertilizer, can actually be really effective at more effective than de-icing salt, since it can work at temperatures below that -10 threshold. However, it's quite expensive. And again, it's that organic material that, you know, we don't want to see too much of in our waterways. And like Anna mentioned, there are agricultural byproducts like sugar beet juice and cheese brine that are great options. They can work at really great really low temperatures, lower than -20. But again, you know, I mean, Anna touched upon it. They contribute to a number of different problems when they accumulate in our water bodies, like eutrophication, oxygen depletion. There are some possible issues with color or odor for some folks who may be sensitive to that. And as a homeowner or as a resident, it's almost impossible to source. It's better suited for those large scale winter maintenance operations. There is also a product called CMA, or calcium magnesium acetate, that you'll see on the market, marketed as chloride free or pet safe, which is really great. But if you read the instructions on the bag, they're actually not very effective. They're most effective at temperatures around -5 degrees or lower. So that's less effective than your traditional road salt. Plus, there are environmental impacts associated with the mining and production of a product like this. So that's something to consider. Now, I don't want to scare anyone by mentioning all of these negative effects of these alternatives. They won't necessarily have an impact to the water system if you're using them on your property, because again, we're looking very small scale. I guess unless you live pretty much directly adjacent to a water body, you won't have to worry all that much. But it is important to consider all of these facts when you're trying to make an informed decision of what might work best for you and your property and your budget. So there are a number of other great resources out there that we can pass along to you to give you a really nice deep dive into some of these alternatives. So if someone were to ask me for my final recommendation on what they can do to manage the salt use on their property, the thing that I would say is to just be smart about how you do it. So don't apply salt if you haven't shoveled the snow already. As I know, shoveling the snow is hard. You don't want to do it, but just save the salt for when you're dealing with ice rather than with snow. You want to try your best to just prevent ice patches as much as possible. So ensure your eaves don't drip or drain onto walkways. Shovel the snow as the sun is starting to set already so that the sun won't melt your piles of snow into ice. And then when you are shoveling the snow, store it in an area where the melt water won't go on paved areas. I like to shovel mine right into the middle of my lawn so that as it melts, even though the ground is frozen, hopefully some of that snow just infiltrates into the ground, as Dr. Clark was talking about, rather than going onto those impermeable surfaces. And then if you've done all you can to prevent ice patches and they still start to form, do your best to treat them without bringing salt into the equation. Create traction using some of those great traction alternatives that I mentioned, or even manually try to remove the ice with a shovel or a steel ice chopper to do your best to minimize how many ice patches form on your property. So you've shoveled the snow, you've broken up the ice, you've tried to create traction, and you still think you need to use salt. Ask yourself a few questions first before salting. First, what is the temperature? Remember that road salt loses its effectiveness at temperatures below -7 degrees Celsius. So if it's a really cold day, spraying salt won't actually help get rid of the ice and will actually only lead to more salt damage. Second, is the forecast predicting warmer weather? Is the sun out? In that case, let the sun do the work for you by melting the ice without worrying about the environmental damages from salt. And then lastly, ask yourself, how much salt should I use? Do you really need to salt your entire driveway, or maybe just the walkway between your front door and your car? And the reason why I bring that up is because more often than not, we are using too much salt. Roads aren't the only issue. Sidewalks have 100 times more salt than what we see being applied on roads. And a lot of very careful homeowners are, of course, using too much salt on their driveways as well. So if you want to picture yourself looking at a square sidewalk block, you really only need to be using about 58 grams of road salt per meter squared. So that's approximately 1 tablespoon of salt for a 1 meter by 1 meter square area of ice. So that is definitely less than what I think I'm even using, and I'm trying my best to minimize my salt use. So be really realistic and honest with yourself about how much road salt you should be using. So if you follow those tips, then you've probably made some really great progress in doing your part to reduce the amount of chlorides in our watersheds, and we thank you so much. So thanks for listening to me talk.
Awesome. Thank you, Tisha. And you know what? I love the last visual of how much salt we should actually be putting outside on our pavements or on our driveways. I think that really captures the idea that we're trying to go from here, that we're not only producing and excavating a lot of road salt, we're using it quite a lot as well. And we can't just depend on all those stakeholders that come before us. We all can take some action as well. Sounds good. Thank you for this. So people have been sending me messages in the chat. And what I'm going to do is I'm going to bring all the speakers on Spotlight so we can have them over here. And then I'll talk about the questions. So, okay, we have a few questions here. Quite a lot for Dr. Grant. I hope you're ready.
I'm always ready.
Awesome. Okay, so I'll start from the beginning. Does those toxins or chemicals that you talked about, have any effect on the trees? For example, littered cigarette butts around a tree, the toxins of the cigarette butts stay in the soil for a longer time. Does that have any effect on the tree, plants, or grass? And also, will the soil be able to handle a lot of volume of water? I just think of grass fields that are sometimes flooded for a while because it takes a while for the water to evaporate and go deeper into the soil.
Well, an answer to the first question, if you have a mature tree or a large tree in the tree pit and the volume of soil is adequate, it's unlikely that the concentration of contaminants is going to be enough that it would actually harm the health of the tree. The contaminants and, for instance, heavy metals is what we were looking at specifically, which can be quite toxic, actually bind to the soil particles and don't move into the tree's root system. So that's good news for the tree. I suppose if there were a pesticide spill or something like that, or a herbicide spill, that would be bad news. Hopefully that would never happen. As far as the volume of water that could enter the tree pit, you want to make sure that you're managing the kind of soil in the tree pit. So if you're designing it specifically to accommodate infiltration, then you want to make sure it's a nice porous soil. So it would have a pretty high sand content, for instance, so enable the water to drain through it quickly.
Okay, awesome. Thank you so much. And that was Yasmin's question. And then we have a question from Tom for Tisha. Does the water control basins where water runoff can happen, can they be released slowly and better, treated through some sort of biofiltration system?
Yes, that's exactly what I think Dr. Clark was talking about. And something that we at TRCA always encourage is, green retrofits and kind of increasing the amount of natural space within our jurisdiction. With that being said, because there's so much impermeable surface, all of that runoff or melt water that's coming from the snow does enter into our stormwater system, which is different from our sewer system. Our stormwater system does not get treated, it does not get filtered. It pretty much just runs through these underground pipes and directly into our water bodies, our lakes, rivers, and streams. So that's the kind of the difference between the sewage system and the stormwater system. And so that's why it's really important that we're managing as much as we can what gets inputted into the stormwater drain. And if that means redirecting some of that flow into some more natural spaces where it can do that natural filtration process, then that helps, but also, of course, mitigating our own inputs as best we can.
Awesome. Thanks, Tisha. I have one question that is for all of you, actually. But before that, I do see some people are leaving the call, which is understandable. It's scheduled till 6:30. We'll go for 5-7 more minutes for Q&A. But thank you for those who have joined us. This will be recorded and it will be uploaded on YouTube afterwards as well. So if you want to catch the Q&A period, you can go to that later on. I'll send an email about that. Question for all of us, and maybe Anna, you can start with answering this one. Should municipalities consider redesign of runoff so that it goes, I think that was the question connected to the water biofiltration system. Do you have any
Yes,
thoughts
of
on
course.
Do you have any thoughts on how they can consider going about it? Like, we looked at a lot of different systems. And we talked about different stakeholders as well, right? Who should they be implicating in this redesign or revamp?
Yes, I think a collaboration with the agricultural industry would be great because there's a lot of native grasses that you can use to filter the water. For example, switchgrass is an amazing grass that can withstand a lot of salt and actually grow on the side of the road. So you can use it as a biofiltration system, which doesn't really add a lot of work. It's just a matter of planting different plants along the roads. So you would see different things versus you wouldn't have to destroy the already built infrastructure. So yes, absolutely. I think there's such a huge need for changes and more inspiration from other countries, because there's other countries that are in the northern climate and they don't all do the same thing. So there's, for example, Finland, and they have a different way of packing the ice, or they have a different system, a more frequent way of removing the snow, so which avoids ice formation. So maybe there's different things, the infrastructure and also how we manage our roads.
Awesome, Anna. So building on that question, there's another question specifically for Dr. Clark. Are there any other cities other than Montreal that you know of that have implemented the larger tree pits? And has this idea expanded to other locations?
Oh yes, absolutely. And in fact, if you're looking for a growth industry, there are companies that actually manufacture the kinds of components you would need to build the special sidewalks. I won't name any brand names because I don't want to promote any specifically, but when the civil engineers then go about building the sidewalks, they'll actually excavate deeper and they'll put in place some modular structures that will hold up the surface of the sidewalk. And those are being marketed widely. So if you go onto the websites of these companies, they're very easy to find, and you can see images of beautiful projects that have been done all across North America and in Europe.
Okay, awesome. Then one more question from Shreya, which is, I'm going to scroll back up. Are there certain plants that can be used to remove the sodium from the soil, which is, they're saying, bioremediation? I know plant species found in mangroves are resilient to salt. Are there any species that might be found in this part of the world? And this goes to all three of you. Anyone can jump in here.
I can jump in first and say that the urban forestry teams of a lot of municipalities, especially here in the Toronto region, put in a lot of time and research and effort into selecting what trees they're putting in as their street trees, like the specific species. So these are the trees that are planted along like the boulevards, along our roads, that the city specifically picks and like hand chooses to put in the right place. And their policy really is right tree in the right place. So those species of tree, if you want to take a walk down your neighborhood or a walk down a boulevard and see what species they've planted, these are all species that are going to be really as salt tolerant as possible, that are appropriate for the specific location. So I think part of the reason for that is, of course, to hopefully remediate the chlorides that are entering into those areas, and also to maximize the success of the plants and the trees that are planted.
Awesome. Anna, Dr. Grant, any thoughts on types of species?
Well, I can make a couple of comments. One is that you want to think about the idea of salt tolerance, right? As Tisha was mentioning, and choosing the right species to put in a place where they might be exposed to salt. But think differently about perhaps a different angle on that question is the idea of phytoremediation for plants that can concentrate the salt. Because remember, the salt, the sodium, for instance, or the chlorides don't break down, right? So it's not just about having a plant that's tolerant or that immobilizes the salt. If it's accumulating the salt in its tissues, for instance, then you have to remove that plant. You have to remove the biomass to take the salt away out of the environment and then deal with it somehow that's environmentally sensitive, right? Maybe put it in a secure landfill or something where the salt is not going to do damage. So there's two things to think about: tolerance of the plants to the salt, but if you're trying to phytoremediate, then you actually have to remove that material somehow.
Awesome. Thank you. Anna, any thoughts here?
I will just repeat that native grasses are perfect for this, and switchgrass, for example, has a really huge, deep roots. They go up to 15 feet. So, and they're able to extract chemical metals, heavy metals, as well as salt. And the switchgrass can be used as a biofuel. So basically you can convert it from biomass into fuel, and then you have a circular economy.
Okay, awesome. So another question, and I'll make this the last question for today's panel. Can we discuss the implication of pulses of salt treatment concentrations in water versus chronic levels of exposure, specifically insect populations?
And I think you may be the expert in that, but I just want to say I've seen an interesting quote from my ecology textbook, which says that it is the extreme events that shape ecosystems. So if we can reduce the magnitude of the extreme events, that's beneficial. But I'll turn the rest over to Ana.
And that's right. And I'll just say that there's no experts. So everyone here knows a lot. I think definitely pulsating, large pulsating concentrations of salt or other chemicals are a lot more detrimental than long exposures, because as you could see from the experiment on mayflies, it only took 7 days for half of the population to die at a really, really low concentration. And now the 4.2% concentration that I was investigating, it may not be realistic. Maybe that's way too much. We would have to do a lot of tests to see if this is a realistic concentration that can be achieved in the environment. But during the melting of ice and snow in springtime, you have a lot of pulsating concentrations of chemicals that are running into water streams. And usually where mayflies live, for example, sometimes they live in puddles of water. And in these puddles, the concentration of chemicals can accumulate really, really high. So it really depends on where you find which insects you're talking about and what time of the year. So during the springtime, you're going to have a lot of high concentrations. So I would say pulsating acute events are more detrimental than long-term exposures.
Awesome, thank you. Tisha, any thoughts here?
Yeah, definitely. So there is a Canadian water quality guideline specific to chloride concentrations in surface water. And of course, the acute threshold is much higher than the chronic threshold. But at these thresholds, that's when you're going to start to see effects in our ecosystems, and that would include our invertebrate, our benthic invertebrate populations. So at those acute levels, where that water quality guideline threshold has been exceeded, you're going to start to see probably more die-offs of these invertebrates, whereas at the chronic levels, which are lower, that threshold is lower. But you're probably just going to see more just population shifting over time and changes to the population. Some species maybe becoming a little bit more abundant while others decreasing. And that all impacts the ecosystem, as Ana pointed out, in very profound ways. These benthic invertebrates, or these aquatic invertebrates, are, they form the base of the food web within our natural ecosystems. And so any changes that happen there, no matter how small or how big, can impact the rest of the food web quite significantly. So definitely something to think about.
Beautiful. Thank you so much. And with this, I'll conclude the panel discussion. Thank you to our panelists who stayed for a bit longer as well to answer all the questions that are coming in. I know I didn't get to all the questions, but people, if you have questions, feel free to reach out to the 3 panelists on LinkedIn, and they can answer your questions over there as well. And thank you for staying for this bit as well. I've taken down all the names. I'll be doing a raffle randomly in the background, and then I'll email you by tomorrow. So please check your email about asking for your address. With this, I just want to leave you with a gentle reminder. think about the image that Tisha showed you at the end as well, right? The square pavement and how much salt we're supposed to use. And think about the salt box that I showed at the start of the presentation. I'm going to bring it up very quickly over here so that you all can see. This is, we put 5 billion packets of this every year in Canada on our roads and highways and streets. This does not include our driveways and our smaller streets. So keep this in mind the next time that you're putting salt out in the next couple of months, maybe next 2-3 months for some places in Canada. If you have any other questions, you can email me at omer.juma@learn.ocean.org, or you can connect with me on LinkedIn. Thank you so much, and have a wonderful evening.